let's actually talk about state space models. What are the benefits of state space models and how do they work?
The big challenges in AI are really like, how do you provide the AI system all of the information that you can in order to get it to reason, understand, operate? And a lot of that is framed as context, right? And there's this notion of like context windows. There's this notion of, can we have infinite context, for example? The big challenge though is like, how does your compute scale with the amount of information that the model sees? And so that's where a lot of the work in architectures is really around making these models much more efficient. So classic transformer architecture, for example, has like quadratic scaling with context. And what this means is just that if you double your context window, you're quadrupling the amount of compute you need. And so if you have very large context windows, you actually are expending a lot of compute in order to run the model at inference. It also is expensive to train for the same reason. These SSMs and alternate architectures are really designed to provide subquadratic scaling. So basically they're saying instead of expending 4 times the compute, you could be expending a factor that's more aligned with the amount of context you have. And so if you're doubling, like you're actually not quadrupling compute, which is very important when you start getting into these regimes where you have massive amounts of multimodal data.
Karan, I'm so excited to have you on. We've actually, somewhat by accident, had so many episodes recently on Barchives focused on audio applications. I think we're in the earliest inning of audio and multimodal applications, and it's been a little while since we've caught up, so I'm really excited to have you here. Thanks for coming on.
Thanks for having me. Yeah, I think last time we met was NeurIPS, actually, in December.
It's been a little while. So the first thing that I have to ask is, I think for as long as I have known you, which is now the past few years, you've had an interest in startups. I want to hear a little bit about that origin story. So you studied at IIT, you were doing RL during your master's at CMU, you went to Stanford to do your PhD. Why and when did you become interested in startups during that journey?
Yeah, I guess, I started working on research in my undergrad, and it was a lot of it was in the beginning around like sequential decision making, RL, this type of stuff. And at the time, like Atari games and like a lot of the RL work was very much in the game playing domain. And that already was quite interesting to me actually at the time, because I used to be a gamer in my high school and middle schools.
I heard you're a serious gamer.
Yeah, I used to really like, sit and do very long gaming sessions all the way through the night into the morning, as I know many people do. But I think that's kind of what actually got me pretty interested in a lot of the game playing type of stuff. But I also worked on other interesting applications. I think like at the time, it was quite clear that there would be a lot of AI work that would become very impactful. And so I always imagined working in industry even before I started my PhD. I wasn't particularly inclined to work in academia just because like I really like working on systems and like building things. I like programming, for example, and like part of the joy of programming is building something that works. And so I think when we were doing our PhDs, I don't think there was an intent really to start a company as much as like we were doing work, and I worked very closely. My PhD advisor was Chris Ray, who and at the time in the lab there was a lot of exciting work going on. Flash attention trees work was happening then, and a lot of work that I worked on with Albert Gu, who's my co-founder now, and who was one of the main people in this area of alternate architectures. So a lot of that work was spinning up. And so I think like the startup route was mainly just it was like a consequence of like doing or being part of interesting work, and then realizing that interesting work actually had a lot of potential highly impact applications. And then sort of like realizing that the only way for us to continue to work together on that was to have a different vessel in which to do it.
Yeah.
And so the company just made a lot of sense because, I've been working with Albert for 5 years. Actually, this might be our 6th year working together. And Chris, and Arjun and Brandon, who are my co-founders that, I've known for many years. So it's like very long-term working relationships, and that's kind of what makes it very interesting, I think.
Totally. So, it's a phenomenal team. Obviously, know Albert well too. But I remember during your PhD, you were working on many different projects. I think we maybe even first connected over Meerkat. Why did you decide, and maybe the answer is the people and these long relationships, but why did you decide state space models? This is the worthy thing of pursuing and spending my full time on after working on so many different interesting research directions and projects.
Yeah, so my PhD was kind of weird because my thesis was on the applied side of state space models. So that was kind of my dissertation. But then during my PhD, I obviously worked on a lot of different projects, and some of those were around model evaluations and also thinking about how to train models that are more robust. And then that led to this whole work that we did on an open source system called Meerkat as well, which was really a data system for doing evaluations and machine learning. I think that work was incredibly interesting, and honestly, like I still think that there's so much interesting work to do on the eval side of things. Even as we're building models at Cartesia, there's just so many things that come up. But I think state space models are a breakthrough, and it's a once in a generation type technology. There's a lot of interesting things that are still left to understand about it. And so that's kind of what I felt like when working on this. It was just like clear that there's just so much meat there.
Gravitational pull.
Yeah, yeah, and I think part of it is just like I think part of being in AI is obviously like I mean I worked on this during my PhD too, which is like you work in AI to build the models, right? That's what AI ultimately is about. It's like these new models that can do these amazing things. And so, as an AI researcher, I think you're drawn to that part of it a little bit, which is that you want to build the technology that enables the applications. And I think the evals work is really important and interesting, but it's a different flavor of work, right? I think it's better served by it's actually a more like systems problem rather than necessarily, um, you know, I mean, there's a lot of AI going on there too, but like I think building a model is just so exciting, basically, because you're creating this capability.
We can talk about evals too when we get into some of the models that you all have built and how do you know that you're releasing good ones. But maybe let's actually talk about state space models. Maybe not everyone will understand, what are the nuances between state space models and other architectures such as transformers. So, in your own words, what are the benefits of state space models and how do they work?
Yeah, I think the best way to understand state space models, really why people even care about architectures in the first place, is to think about like what the main trade-offs are when you are actually building AI models. And so I would say like one of the big things with AI systems after 2016 and transformers is a lot of the stack is built around this self-attention transformer architecture. And the big challenges in AI are really like how do you provide the AI system all of the information that you can in order to get it to reason, understand, operate. And a lot of that is framed as context, right? And there's this notion of like context windows. There's this notion of, can we have infinite context, for example? These are some questions that folks might have heard of. So I would say the big challenge though is like how does your compute scale with the amount of information that the model sees? And so that's where a lot of the work in architectures is really around making these models much more efficient. So the classic transformer architecture, for example, has like quadratic scaling with context. And what this means is just that if you double your context window, you're quadrupling the amount of compute you need. And so if you have very large context windows, you actually are expending a lot of compute in order to run the model at inference. It also is expensive to train for the same reason. But these SSMs and alternate architectures are really designed to provide subquadratic scaling. So basically, they're saying instead of expending 4 times the compute, you could be expending a factor that's more aligned with the amount of context you have. And so if you're doubling, like you're actually not quadrupling compute, which is very important when you start getting into these regimes where you have massive amounts of multimodal data. So for example, large volumes of audio, video, etc. I think that's one regime that's really interesting. The other regime that's really interesting is long-running AI systems. So imagine that you have a personal assistant and that assistant is actually designed to run for 100 years, right? Now, that's going to be really difficult if you can't actually put context into it or information into it constantly and have it remember it. And that's like a big challenge with these systems today, because that's why you see, like, if you interact with any standard system, it's mostly off all the time, right? And then you turn it on and you like interact with it and you turn it back off. I would say like one of the things we're very interested in is like systems that are on by default. So they're always running and they're always ingesting information, but then you can turn them off sometimes. So I think that framing, like changing that sort of um interaction pattern is sort of like what it's really all about. So these alternate architectures are really just it's a tool that will allow us to build systems that are fundamentally more efficient and that can scale with more information. I think that's really the heart of it. And obviously, SSMs are a specific type of architecture that Albert really pioneered, and Mamba is kind of like one of the more recent version of that. And it's really just like really interesting work. One of the key technical tidbits there are like, I think a lot of these alternate architectures embrace compression rather than embracing, let's say, retrieval as the paradigm. So they really embrace this idea that like, much like the brain, like you're compressing information as it comes in, and you're able to sort of consolidate and abstract it in a very natural way. That's a very deep and interesting idea, I think, and it's going to have there's a lot still left to be done there. But I think that idea of like, as information comes in, you're going to compress it, update some memory, and remember it. That's the heart of it.
This is a perfect segue because we talked about compute efficiency. There's also no free lunch. So compression can be great in some cases, maybe in others, it's less good. So I'd actually just love to hear what you think state space models are less equipped for. And then I'm bearing the lead a little bit, but I've heard you talk about different data types that are better and worse suited for this. So
yeah, I think there's so much work that we have to do to understand like where these models are strong and useful. I think that what's clear from the way that they've been built, just from the ground up, and even like the actual like mathematics of these models, is that they are particularly good at signals and modeling signal type of data. What a signal basically something that's acquired by a sensor. So it's some sort of analog signal that's been acquired by sensor. And so one example of this would be audio, right? Which is the type of models that we build at Cartesia today. Another example is video. Any type of really signal that you can imagine is really good for these models. And so I would say that when you look at the strengths of the models, they're really all about like how to take massive amounts of signal data and then be able to sort of compress that. And this is not strange because compressibility is really a property of signals. This is why, for example, even if you look back at audio research for the last like many decades, a lot of it was around like building these feature representations from the raw signal that mostly capture the information in it. So they compress the signal in some way.
yeah, and I feel like a lot of the OGs studied signal processing and
That's right. So a lot of it based on like the Fourier transform and things like that. And then, there's like other sort of like structural things about like the human ear, for example, that you can use to understand like how to throw away information about speech. Like there's all kinds of interesting, weird things that folks do. But a lot of it is because fundamentally the signals are compressible. A lot of the information in the signal can be preserved even by throwing away a lot of the data. So the volumes are large, but there's a lot of compressibility in there. And so handling that, I think, is very, very much where these models are very strong. So they can take in massive volumes of data, massive context, and then be able to sort of suck in all the information and abstract it very well. That's where they're very strong. I think where the world has been very obsessed over the last few years is language modeling specifically, where transformers have done really well and they've been scaled. We actually don't even know if SSMs are good or not at language in some sense, because no very large scale SSM for text exists. There's actually some reasons to suggest it might have some interesting properties.
maybe I'll just ask because you've mentioned a few times that there's so much more to learn about SSMs. Like kind of what is the max scale that you have either trained or seen, I assume?
I think that there are large SSMs out there that are like order 100 billion parameters. and which are very large, right? And so I think these models scale well. Like ultimately, like the goal of architecture research is not to try to necessarily like violate the sort of empirical principles that are sort of that have been established, which is that you can't beat scaling with data and compute. I think it's like actually embracing that, but then understanding like how to structure the problem better so that you get more efficiency for the same quality. I think that's really the goal of architecture research. And a lot of the algorithmic innovations are about how to blend that with hardware and systems in order to get the most out of these models. So yeah, I would say like it's clear that these models can scale to very large size. I think what's less is that a lot of what building models requires is taking a lot of reps on some problem, and so doing like a huge number of reps to see like where you can get to. So I think that's where of course at Cartesia we're doing a lot of work on specifically like audio and multimodal data, but I think that's why I keep saying there's a lot to learn, because it's really about how many reps have folks taken on transformers and so on. There's a lot has come out of that, and I think similarly when more reps are going to be taken on these new architectures, a lot will come out of it. And I think they have very interesting sort of properties that I think make it quite obvious, I think, to at least us, that they will have a very important role to play in a lot of the AI models that are going to be built in the future.
Okay, I'm so curious about a lot of what you said, including like what are the different things needed in order to get more of those reps in the ecosystem. But because you explicitly mentioned hardware, I do have to ask a little bit about what you're seeing in hardware land that, right now, because there is a strong attention transformer language model moment, a lot of the hardware is also accommodating that. So how do you think about it?
Yeah, I think we sort of are lucky in the sense that um the hardware of choice has been GPUs, which were designed to do which meandered their way through the history of like the last 25 years of computing to solve a variety of different workloads, and are used in scientific applications and games and so on. So I think like, but maybe by accident we happen to have a um the default hardware on which most of these models run is actually so immensely reprogrammable and has so much support for many different ways of doing computation of different types that it actually worked out pretty well. So if you're building with state space models, you actually don't necessarily not benefit from the advances that are being made on the hardware side. I think that's like an accident of fate, actually, right? That these GPUs and so on.
If it works for you, then great.
Yeah, yeah, exactly. But the fact is that they're actually quite good for running non-transformer models too. For example, we were for the last 12 years, convnets have been huge, and obviously we're in the last decade we're actually mostly driven by GPUs, and GPU acceleration in deep learning was at least initially mostly done on convolutional neural networks, not
Yep.
transformers. And so actually there's a clear connection between a lot of the models that these alternate architectures are versus like what the old models used to be. So the alternate architectures like SSMs are very related to convolutions. They're very related to recurrent neural networks, and these have been around for a long time. So I would say the hardware has been evolving with models that look quite similar to SSMs for a long time. Um, and actually transformers were quite different from that when they came out, because they were designed quite differently and so on. So I think hardware side, we sort of mostly think a lot about the software layer of that, and really kind of like how to better support natively the types of models that we're building on the hardware. But I think like generally speaking, it's been pretty smooth sailing, I would say. And I think a lot of the hardware companies are actually pretty supportive and like excited to help develop new types of models.
Yeah, they don't wanna be left behind, so they probably
Totally. And
allocate
I think
a portion of research to, "Let's
exactly.
make sure that we're on top of this."
Exactly. And so many people there are actually just like researchers themselves that are working on these problems. So like it's almost like they're also part of this ecosystem anyway. So that's why they care about it too. So I think overall it's been pretty positive there. It's like a more research community effort.
Awesome. Well, okay, really helpful context on state space models. I'd love to get a little bit into the actual company building in Cartesia. So I remember, when the research was there, but the initial application and modality wasn't. So take me through how you guys landed on audio as your focus, as your
Yeah.
initial focus.
Yeah, I would say so in our PhD we wrote this paper, me, Albert, Chris Donahue, who's now a professor at CMU as well, and Chris Ray was there were a couple of Chris's on that paper. I actually called Sashimi.
Always need a few Chris's on a paper.
Yeah. So there was this paper we wrote called Sashimi, which was the first time we applied state space models to audio data. And there we were actually training models on raw audio, which has been an interesting area where actually WaveNet, I think, was one of the early papers that made progress there from Google. And there's been a ton of work in understanding how to apply different types of models to raw audio. But I think one of the fundamental challenges of raw audio is that you have about, I think, approximately 1 million samples in a minute of raw audio. So you actually scale the amount of information you have in terms of sequence lengths and context is actually scales very, very fast because audio is sampled at a very high sampling rate. So um, I think that paper specifically really kind of was where we felt like, oh wow, like these models really work for audio. Because when we were running experiments and stuff, like empirically, the performance was amazing. And so, that paper is obviously an archive, and folks can check it out. But that really got us thinking about like the application of these models to audio specifically. And so when we were starting the company, I think we were really interested. Fundamentally, we've always been interested in like this question of like how to train efficient models and make them more attractive. And so it was quite natural to think about applying this to audio because we really felt like it's really where multimodality meets the perfect application meets like the a place where we can actually do a lot of research quickly. So audio is also like the cheapest signal in some sense because it's like a 1D signal that you can do a lot of research on. So from a research problems perspective, it actually shaped pretty simply, and you can work on like fundamental kind of primitives. And then from a commercial perspective as well, it's like quite interesting because there's so many applications in real-time audio that are spinning up. And at the time, actually, there was much less happening. Like a little over a year ago. Now there's a lot happening in voice, but um, that was kind of what was really interesting, which is like, how do we enable low latency, high quality models that run on top of these architectures that are super duper fast? And so that was kind of the starting point, I would say.
You're right. I think we're in the early innings of people are really excited about audio, and I think it's going to unlock a bunch of really, really cool applications it already has, but we're still in early innings. How much did you look at competitive landscape when you said, "Hey, we have this alternative architecture, we're training a model"? There is a narrative that looks like the big labs have a ton of money and they're pouring it into multimodal models, but I think at the time in which you were starting Cartesia, certainly text is kind of like the winner of where capital is being allocated. So how much did you look around and do a market pulse versus follow your research and intuition and just see potential customer demand in the future?
Yeah, I think we obviously looked around a little bit, as one does, but I think one of our takeaways was we wanted to work on things we actually believe in. And that's always been very important. It's just like, I don't want to work on anything where I'm not like, I can see this being a thing that I would be doing for the next 10 years. And so I think audio fit the bill because we felt like it aligned with our larger research vision for the next, 10 years. And which I'm happy to talk a little bit more about. But I think like the other part of it that was, I think, interesting. I mean, you talked a little bit about the big labs. Certainly, like there's so much interesting work happening at all the big labs. Like, and I mean, I was going to name all of them, but everybody already knows them. So
You know who you are.
yeah, yeah, they know who they are. But there's so many brilliant researchers there. I think that one of the things I realized is that building something even something small is very hard. Building product is extremely hard because you have to be very obsessive about really delivering like the best quality. And even doing it for something small is so difficult. The reality is that like, obviously resources are great and helpful. I think what I've observed in research is that really breakthrough ideas can come from having very large constraints put on you. That's really where a lot of great that's why, academia does great work, because they don't have access to that much computer resources, and they work on problems that, maybe don't even matter today, but might matter a lot in 10 years.
I absolutely see this in venture too. Like constraint allows for focused decision making and
That's right.
100%.
That's exactly right. When you have a lot of resources and capital, you can do a lot of things. And that means you might also not think as critically about what is the sort of like most efficient path to doing many of those things, because you're not very constrained by capital. I think that for startups in the space, there was almost this like, I felt like being in academia specifically, there was almost despair in some sense that like, you know, um, the big labs are going to do everything, and like nobody else has essentially a place in the world, especially in AI, where building the models is obviously, like I said earlier, is like a very core part of doing AI. I think we just don't believe in that. Frankly, I think maybe some people would say, hey, like it's, foolhardy to try to build models in a small company, but I think actually like I think there's never a better time to do anything new than now. And more or less, like I think even 20 years later, there'll be new model companies spinning up that do new work that big labs, maybe we'll be the big lab then, will not be doing. And I think that's the right way to do things. So I would say that we're pretty excited about a lot of these directions. I think it takes a huge amount of work and effort to actually realize anything. I mean, it takes like years of sweat. So I think that's why I'm not super worried. I think you have to have very deep conviction in something to actually get it over the line, basically.
Yeah, 100%.
That's kind of where we see ourselves. And that's why, like, for example, when we started in audio, we were like, yeah, this is going to be the first step, but we're going to have to be obsessively doing this for a while. So we need to really believe that this is kind of a core modality that we care about. And I think we do, because we think voice interaction is so fundamentally interesting, because, obviously a lot of what we do right now is interact through text and chatbots, which are great, but they just don't have the visceral feeling of interaction that speech has. And so I think like getting these long running AI systems that can talk and listen and do things, it's pretty interesting.
Yeah, I agree with you. I mean, I think on the phone, we're going to be talking more to machines than humans in shorter period of time than we realize.
Yeah.
So tell me a little bit about what are the models that you built today and offer today in Cartesia? What do they do?
Yeah. So our first set of models has been focused on text to speech. Now, text to speech is pretty interesting because it feels like a fairly simple task, right? Like you're given a text transcript and you have to produce like very natural sounding speech from it. It's an extremely difficult problem, as are most things in AI, because depending on how you work on this problem, you can really kind of have different trade-offs that you make. And so we've been really focused on the low latency side of this. How do you produce speech extremely fast, but very natural and very high quality? And so I think that part of, building that has been like going really deep into the way in which folks build streaming models, specifically for multimodal data, and then really innovating there on the model side and also on the actual end-to-end training and in building these systems. So that's kind of what we've been doing. The text-to-speech model we have right now called Sonic is it's currently the fastest model that you can get in any region of the world. We basically have optimized latency and got it to be incredibly fast for production use cases.
So let's actually talk about that, because the number one thing I hear from people building audio applications, I hear a lot of complaints, but one of the complaints that I hear is latency. Like the latency is not good enough. There are other things around naturalness of the conversation, but some of that
Right.
corresponds with latency. How can you,
Yes.
that is a subset of the naturalness problem. And so I guess what has been the biggest challenge in reducing that latency?
Yeah, I think latency, part of it is like just how do you design models to be fast? How do you give them information and then have them respond instantly? I think that's just a algorithms architecture problem. And a lot of it is about like how information gets ingested in the model and how it's processed. So that's one side of it. And then the other side of it is the system side, right? Like how do you actually build your inference engine, your platform in order to support low latency inference? Because that's a workload that's quite different from, let's say, a chatbot where latency is actually not the biggest constraint.
Yep.
Because you might be reading and words are generated, but in the audio side, actually, because you're generating raw audio, it's like a huge amount of data. And you're streaming this all out. And like, if you, for example, miss and you're too late on a chunk of audio, it's going to be missing in the, like, you're listening to a conversation, imagine like it just cuts off, right? Like that doesn't quite work, right? Like that's very odd. So I think the thing that makes audio and voice challenging is that you're putting something in front of people ultimately, and they're going to interact with it. So the bar for naturalness and quality is very high, very, very high. And so the latency side of this is basically about like the models, the systems engineering, etc. You're right. A lot of folks are really their biggest complaints are generally around latency, because I think like a lot of voice AI, maybe like 12 months ago was more in demo stage. Now people are really thinking about production. And when you think about production, like then thinking deeply about the models actually starts to matter so much more, because basically now what you have to worry about is like, I'm going to be doing this at like million billion scale. How is that gonna work? Right. And I think that's where like a lot of the work that we're putting into the systems and the actual models will be very important.
100%.
We're a young company, relatively speaking, like been around a little over a year, but like I think we're really thinking deeply about like what will these systems need to look like, because voice deployments will take, some will happen this year, a lot next year, but it's going to take a few years for like everything to permeate. And so in the meantime, what we can do is be prepared for the scale and the volume that's going to come in, and be able to support all of that. And so I think that's going to be really interesting. The interactions, et cetera, are going to be interesting. But yeah, that's what we obsess about, I would say.
Yeah, no, I'm excited. I mean, I've heard people hack everything from filler words as you kind of wait on your latency to
Right.
smaller models that respond right away, hopefully are relevant enough, and then stacking the larger model afterwards. And so 100%.
There's a lot of tricks. But our take is, there's a lot of tricks. What we want is to bake it all into the model.
Yep.
Just have the model do everything.
Yeah. Why, stack or add unnecessary steps if you basically want to reduce latency as much as possible and then make it natural as much as possible.
Exactly. And then I think like, I mean, if there's one lesson in AI, it's that let the model do the work.
Yeah. I also took you away because we were talking about the models in Cartesia. So you were talking about Sonic.
Yeah, Sonic is the fastest you can get for production. And so we're doing a lot of work there to continue to sort of improve the models and make them even better, as well as reduce latency even more. And so we recently released like even faster models that are like we used to have 90 millisecond latency. We're dropping that down to 45, and basically we're trying to bring latency down to more or less close to zero, like floor, because I think that at some level there's a principle here, which is like if you can, even if like let's say somebody told me like I need this model to be only 30 milliseconds and no more, I would still push and say like let's try to make it 15 and 10, because I think there's so many things that you can make room for when you make latencies go down, that are interesting, and you learn a lot by doing that. So there's a lot of science there that is actually quite helpful on the efficiency side.
Is it fair to say that your number one priority right now is reducing latency when it comes to model changes?
Yeah, I mean, latency is definitely one part of it, and then the other is, I think, continuing to understand how to build these models to be more interactive, more natural, more conversational. That's kind of the two axes that we're thinking a lot about. And then I think on the, if you look at Cartesia as a team, like we have, we do sort of research, and then we are building these models and putting them into the hands of customers. So we have a platform team and a product team as well. So but we're pretty lean, like we're not 100-person company. Like this is like, 25, 30 people that are working together on this. So the research that we're doing is really like, is really core algorithmic improvements to models, and like making models better for every modality, right? Like it's not just audio, actually, it's like core deep learning research. And then on the applied side of this, we're building these models that are actually going to be in the hands of customers. So I think that combination is really where we're investing a lot of time, because that's what we've also been doing historically in academia. And so that's kind of what one thing we're excited about, is to build that core research team that's excited to take forward this agenda on efficiency, on architectures, and on also other challenges. It's not just architectures. There's a lot of challenges in AI that we're excited about.
Amplify well. We have a lot of investments that span academia and industry. Some companies do it really well. You all have managed to strike a balance between moving unusually fast and also having a research heavy company. So I would just ask a little bit more on like, how is the team structured? Do you have tips on how to do that effectively? Maybe I'd also ask, because this is another thing that comes up, part-time co-founders in academia. How do you navigate that?
Yeah, I think those are great questions. So, first part, I think in terms of team structure, I think, um, honestly, we're figuring it out as we go as well. I think that one of the things we do is we have a pretty flat team structure where we have like pods, and we have basically every pod has a founder assigned to it, and so there's even in research, for example, there are projects going on, and there's just self-organized in to some degree, and then we just have very talented folks working there that are able to sort of navigate the uncertainties of being part of a small team, right? Like things move fast, things are flying left and right, but you're able to net move quickly to get things done. That's kind of the vibe, I would say. But obviously, like, it's also like we have a brilliant chief scientist, Albert, who's obviously a very sharp research mind. And so he, I think, has great intuition about, I think his biggest, thing is like he has amazing intuition about things that work and things that don't, and very good taste in research. And so he's able to pick the right problems to work on, which is the whole game in research actually is like picking the right problem. And so I think that's what he does a lot of, is like making sure that we're working on things that will really matter, both for our models and for the future research that we want to do. And so those are on the research side. I think that combination is really what makes it possible to do both amazing research work, and that is needle moving for our models, and having things be relatively organized. That is really the secret, I would say, is just having Albert there to really steward all of that.
Steer the ship.
Yeah, he's steering the ship. And then on the part-time co-founder side, I think, like, obviously Albert is chief scientist here. He's also assistant professor at CMU, where he has a great lab that works on the academia side of this, which is really, I think in academia, it's really all about like problems that may not have commercial impact even for 10 years. I think that's like kind of what they really spend their time on. And I think that's right and appropriate. And like they actually do very interesting work because of that. But I think it's like relatively easy because I mean, it's just like, it's so entrenched. Like I have such a long-term working relationship with him that it just makes it really easy. And even Chris, who's also a co-founder and like runs the lab at Stanford, like, I know these people since like 5-6 years. And so I think the ability to have very high bandwidth communication with them and be able to sort of interact quickly day to day, and be able to get what needs to be done across the line. That's really what matters at the end of the day. They had, this company wouldn't be what it is without them.
Yep. But you have the kind of long running history, kind of like a state space model. You have
Yeah, that's true. That's true.
rely on
That's
the last 6 years of data
right.
and keep where
That's
you
true.
left off.
Yeah, the 6 year data really matter. And obviously it would be really hard if we like had worked together for 3 months and then we're doing this, because I think it would just make it really difficult. But like, I think that we have like, we so deeply understand, I understand their working style so deeply and they understand mine so deeply that like, there's no like, there's no time lost in trying to like translate things. It's like very instant and obvious.
I heard you give everyone on the team personal Yoshis. Why do you do that?
Yeah, we give everybody Yoshis. Albert is in addition to being chief scientist, is also the culture ambassador of this.
You're the culture carrier.
Yeah, he's a culture carrier, and like he's been he's had a lot of pet Yoshis over the years. And so we wanted to bring that into the company and have everybody get a pet Yoshi. So we have an immense number of Yoshi emojis in Slack, just ungodly number of them. So I think it's just part of the culture, honestly. Like we thought it was very fun, and everybody's desk has their little Yoshi perched on it.
So it's not that Yoshi has some deep meaning; it's just to add some fun to the mix too.
You know what? I should ask Albert that. I'm sure there's some deeper meaning there, but I've never bothered to inquire.
We'll bring Albert on and we'll interrogate him. Where did this come from?
Yeah, it definitely needs an interrogation of some kind, but I think it's mostly a fun thing for us to bond over.
You have this research side of the org. You also have co-founders who are deeply embedded still in academia working on the longer term problems. So you're able to see kind of where is the puck moving in the long term, and then what do we do with it in the short term. And so you balance that with a team that is also quickly executing, learning from customers. We talked about latency as one of the big problems that you hear from customers, but I'd love to just hear, broadly, what are you seeing from customers, both in terms of the spaces that are adopting audio models first, but also in terms of the capabilities that they want more of, which we touched on, but I'm sure that there are more. There are always more asks.
Yeah, I think in terms of the customer side, like there's really two sides to especially the voice space. One is in conversation and one is in
Yep.
creation. We've been
Yep.
specifically more focused on the conversation side of this because um a lot of our sort of like core research is really helping enable like the low latency interactions, for example, right? So that's really more in the conversation side. A lot of folks who are doing creation get value out of her models, but I think it's more off label in the sense that like we're really trying to design for these conversational use cases. I think they're like the adoption that we're seeing is a lot of like telephony use cases are like one of the big places where you're seeing this both for inbound and outbound calling. Um, I think it's like a whole like structural reorganization of how voice is used to do a conversation with businesses, right? I think like if you think about the standard way businesses talk to customers, like it's through contact centers. A lot of that industry is really thinking deeply about like what's going to happen with these AI systems and how is that going to change the actual software that needs to be built and deployed, basically. So I think like part of the opportunity that they're seeing and that we see is um, just having agents work on more important stuff and being able to have AI calling deflect just time away from that and actually handling a lot of it through AI agents as well. So that's kind of one area of like I think deep work that's happening. And so, for example, they're like we've been working, for example, with Cresta, who are building, conversational agents, and they're thinking deeply about how to help these contact centers, right? So that's kind of like one big side of it, right? It's really like how do a business talk to customers, and obviously that's a global thing. Every country, every geography, every language, it's going to require models and infrastructure to support that can scale with that type of volume.
How do you all think about training data given that, like, you have these localization, cultural challenges? We didn't
Yeah,
actually talk that much about your training pipeline. We talked mostly about, like, systems and the latency challenge, but you need data to
yeah.
make a good model.
Right. I think there's a lot of challenges with historically with speech models and multilingual data because I think historically these models have worked well in English but have struggled to be as good on um, any other language really. And so part of what we are doing is really focusing on like building better models for Spanish and French and Hindi and like lots of regional languages as well in order to enable the same quality that people get in English. I think that's really important, which is like you get used to like if you're a native English speaker, like you are and you're interacting with these models, like even you will find still some idiosyncrasies that that we're constantly improving and getting better at, but you will still be fairly pleased with the experience because you're going to be like, wow, like this really works amazingly well. I think when you're talking about other languages, actually, like and speakers that and we happen to have like I think coverage even inside Cartesia about 10 languages. I think that folks here speak, and so they're able to test our models actually themselves and kind of provide feedback. And I think what we've seen with speech models is really like they lag like the English quality. So that's like where we've been spending a lot of time as well.
How do you curate the multilingual data?
I mean, a lot of it is just going out and finding sources of data, and like in a lot of these cases, we would even like start spinning up like operations in these countries to actually start to understand how to collect data. And so I think that ultimately, like we want to solve for the long tail of problems that will happen in each of these languages, right? So if you're on a phone call and you want to say specific acronyms on those languages or specific names and entities, essentially, this is, again, very classic machine learning problem, handling long tail of entities, and will recur here. But now we have new tools, like we can pre-train, etc. So that obviously all helps. But I think that that's really the challenge. And so the customer side is really that, right? Like, how do you build models that ultimately, in a conversation that's live, deliver value? And it's not just about like, hey, the model's fast. It's really like it's fast at scale, firstly. So like million billion scale,
And it can be
responsive, and then it gets all those things right, which is like quite tricky. So that's what we're like hyper obsessed with, I would say, in terms of like how we're training these models. And then I think outside of that, like, I also think there's a huge opportunity for voice to be like a computing interface and a interface for businesses in other interesting ways. So for example, for computing, I think like this is going to be the default mode in which you interact with robotics and with computers, actually, because just the bandwidth of like information that you can provide through voice is very high. You can say one word and it will carry a huge amount of meaning because your tone, the way you speak, everything carries so much meaning there that you can communicate a lot of information very quickly, especially when two people have shared context. So obviously that's a big part of this. And I think like making it really easy to build in voice into computing and other interfaces is going to be very interesting. So that's why, for example, we do a lot of work on device as well, which is really about like taking these models and then running them and on phones and desktop and laptops, everything. And part of the on device effort, at least at Cartesia, is all about um, hey, we know that we're doing all this research to make models more efficient. This is really aligned with this idea that they're going to run on very cheap hardware. So that's kind of the story.
I totally buy that thesis. I mean, a lot of what you said, first of all, you can ask anyone at Amplify or really any of my friends. I'm obsessed with voice notes. And when I get one, this is kind of a hot take because not everyone likes them. It feels like Christmas. It's like listening to my friends doing a podcast, and I get just so much more tone and information than I do in text. So I really buy that. And you touched on two different things. One is sort of this really common telephony use case, which I would say also on the venture side is the most common audio application that I see today. Customer support, contact centers, etc. There's kind of computing interface, which could touch that, but just the idea that voice will be what you interact with in the physical world too, or in other places. And so having it be on device, on edge is important. And then you mentioned creation, which I assume looks closer to things like gaming and avatars and like creating worlds where you care about voice in some way. So those are like the three main.
Totally, exactly. And I think creation obviously is also very interesting. A lot of the work that we're doing on device, part of, we've been very focused on the conversation side, but the reality is conversation can also happen inside a game. It can happen, in all sorts of different contexts, digital avatars. So
I was going to say these aren't like MECI categories, but they are broadly helpful. But they're not mutually exclusive. Yeah.
Yeah, exactly.
A lot of what you said also resonated with it sounds like a lot of this is actually collecting high quality data. And I think, we're brushing up on time, but maybe another time we could talk a little bit about the data collection, which I think is fascinating. But this is something I worked on internationalization, and in the text world, there were periods I went to the Philippines and sort of learned firsthand how common Taglish is, which is a combination of Tagalog and English versus just using Tagalog. So I know that that's something that you care a lot about too. How do you take these bilingual folks and kind of merge it together in more colloquial tone, which is not something I've seen a ton of before.
It's very astute, but like I think like a lot of the internationalization is really like blends of languages. For example, Hinglish, Taglish, Singlish, Spanglish, all of this stuff that where you're mixing this stuff. And that's one of the things we've been doing with our models actually is like you can actually use them with these mixed languages. And that's been a really interesting sort of like area where we found.
Does that look like finding data sets where folks are speaking in those mixed languages, or is there
exactly.
some learning you can do from each language?
Yeah, I mean, I think it's some combination of both, and I think the like interesting sort of like cultural context as well there is like quite cool too. Like, I grew up in India, so I'm also a native Hindi speaker, and so I in India, when I talk, I'm speaking like English, and then obviously that has like very weird, not just patterns of speech, but also has like these idiosyncratic things that come from cultural context too.
100%. Yeah.
Yeah, capturing that is like quite nuanced and interesting. So I think, but that's what it is required to get to the level of realism that I think speakers would expect.
Awesome. And I want to ask because, we had talked earlier about evaluation of systems, and I promised that I would ask. There was just so much to talk about. How do you actually evaluate that the models that you're putting out into the world are good?
Right.
Everything is a trade-off. What are you looking for? And then, how do you actually do that evaluation?
Yeah, so I think like there's three types of evaluation. One is you do evaluations on the model by building a whole suite of metrics in house that that try to capture different aspects of speech and really trying to understand like and even the metrics themselves are a research area in some sense. Like how do you understand generative models is a whole area of like research, right? And so for speech as well, that has like specific implications. Then there's the how do you actually, when you're putting a model into production, you have to do some final staging and testing. And there's a lot of work we do in human evals and really understanding deeply like what these models are can or can't do. And then finally, there's no substitute for customers, right? Because I think at the end of the day, the best feedback we get is from people using the models and then telling us, because they're doing all these use cases at volume, and they're really kind of like drilling deep into specific use cases. That's like the type of feedback that I think that we get, obviously, that's not substitutable by us, tinkering.
Has any feedback just totally shocked you from customers?
I mean, there's been like I can't talk about much of it, but I would say yes. And like a lot of the feedback has generally been like, very interesting, very much like things where we hadn't caught many things because like it was just not specific enough in some sense. But what we've used that to do is kind of build a very, good picture of how to measure these models. And obviously, like given my background doing evals research, this is something I care a lot about, and I'm generally opinionated about it too. So I think like we want to build like very good, concrete things. And I think as an organization as well, actually evals are the way that you get alignment across research, applied research, product, all of that.
But it's cool. You ship quickly, you learn something that you didn't think about from customers, and then you add it back into your human eval data sets or whatever it may be for the next time you ship a model. Or you say, we don't care about that use case right now
Yeah,
because
exactly.
life moves fast and we'll get to you in 2 years.
No, totally. You opt in or out, but I think that's like that's the big lesson there.
Okay, so we're going to wrap here. I'm just going to ask you one more question. Thanks so much for coming on. As I feel like so much has changed since I met you when you were doing your PhD. How have you changed as a leader and as a person since starting Cartesia? No pressure.
No, I mean, I think I definitely have a few extra gray hairs and like a lot more responsibility now.
You can't tell.
Yeah, you can't tell, but a lot more responsibility now. But I think I think not much has changed in terms of my passions for research and for technology broadly. I think actually like one thing I've learned in running a company is it's like actually pretty important. And having talked to a lot of founders, like finding authenticity in your style of running companies is pretty important. Like I feel like it's really hard to mold yourself to be a different person, and you shouldn't. And so actually what I do is just lean on where I know I care about things and I can do them well, and then help people in the company be successful. I think that's ultimately what it is. I actually really like working with people. That was, the way I've mostly done my research is finding interesting people to work with. That's how I started working with Albert.
I was going to say it worked really well. And now you have these like amazing long-standing relationships and
Exactly. And so I think I view the company in the same way, which is like we are bringing in people that we will have for the next 5-10 years, and they're going to work with us. And so, it's really like, how do you compound that? And I think that's the thing I'm most fascinated by.
Awesome. Well, thank you so much for coming on.
Thanks so
This
much.
was so fun.
Yeah, this is totally awesome. And thanks for having me.